Hi there, folks. This is the Algebra 1 Unit 4 review, and I am the amazing Mr. Jansen, so away we go. If we look at these first couple, we're just matching the graph with the table, and as we look at this graph, like if I take a look at the first one, I notice that time increases, and then the height increases slightly. And then once again, time increases again, and then the height increases even more than it did the first time. And then time increases again, and the height increases even more than it did the first couple times. And so as I look at this thing, the time is increasing pretty consistently, about the same amount of time from one point to the next, but the height is getting bigger and bigger in terms of the differences. And so as I look at these tables, it looks like this guy right here, see, I have a change of 1, and then I have a change of 2, which is slightly higher, and then I have a change of 4, which is even more of a change. And so as time increases consistently on this one, it's just going up by 1 each time, the height is getting farther and farther from the original. So this one matches number 1. So I'm going to say letter B for this guy. All right. For the next one, it looks like as time goes up the first time, this actually decreases, and then as time goes up, it increases, and then time goes up again, it increases. And it looks like the decrease and increase are pretty similar. The first one is a smaller increase, but then the smaller decrease, but then the next two are kind of about the same in terms of the increases. And so as I look at this thing, again, time is going up consistently. When I look at this one, it goes up 1 each time. But then here, this one goes down 1, and then it goes up 2, and then up 2 again. And so that really models what I was talking about in terms of it went down a little bit, and then it went up more than it went down, and then it went up about the same amount the next time. So this is letter C right here. All right. And then this one, as we look at this guy, looks like it goes over and then up, over and then up. And when we look at the over arrows here, the over arrows kind of show us about the same amount of time passing. But then the up arrows, when we look at these up arrows, it looks like the up arrows are about the same amount of increase as well. So what we have is a kind of a consistent increase in time and a consistent increase in the height. And so when we look at this guy, it's going up by 1s each time. Over here, this is going up by 5s each time. All right, so this one's consistent, and that's what makes this thing linear. So that's letter A. All right, so just matching those up. For this one, we want to draw a table, then do an equation, then do a graph on this thing. And really, we're just comparing the number of trapezoids and then the perimeter of this thing. And so the first thing I do is I set up a table. I'm just going to do it in terms of X and Y. And so when I have one trapezoid, if I count up the distance around this thing, it gives me a 10. If I have 2 trapezoids, again, when I count up the distance around this thing, it looks like it gives me a 16. And then when I have 3 trapezoid, it looks like, once again, when I count up the distance around this thing, it looks like it gives me a 22. And so hopefully we can look at the pattern and say, okay, it looks like it's going up by 6 each time. This would be then a 28. And so now I want to write an equation for this thing. In order to write the equation, remember, the thing that it's going up by, essentially when we look at this guy, this is going up by 1s each time, so that's consistent. This is going up by 6s each time, that's consistent. So know this thing is linear even before I graph it and all that. But then when I look at this thing, since it's adding 6 each time, since I'm going up by 6 every time, really that's like what I'm multiplying by. When you add 6 over and over again, that's multiplication, so it's y equals 6x, so that's the thing I'm adding each time. And then the other thing we can do, so there's 2 ways to come up with the other value that's part of our equation. You can either kind of look at this line right here and think, okay, what would be right here in terms of 0, in terms of my xy chart? And if you continue that pattern going the other way, like if I went from the 28 down to the 22, down to the 16, down to the 10, if I went down another 6, it would bring me to a 4. And over here, same thing, as I'm going down by 1, brings me to 0. So that gives me a plus 4 over here. So the equation is y equals 6x plus 4, so it's the thing I'm adding is my multiplier. The thing that's paired up with 0 is what I add onto the end of this thing. But then really, the other option here is once we come up with that 6, you can plug a value in. Like I could plug the 2 in here and get 6 times 2 is a 12. Well, I need to add 4 more to get to the 16. You can kind of think of it that way as well. All right? And then in terms of the graph, I'm just going to scale this thing. So I'm just say like 1, 2, I'm going by halves really, 3, 4. And then over here, I can go by whatever I want. I think I'll go by probably 6s, since that seems to work out okay. And I'm just going to do like a little zigzag here. And I'm going to start with a 4, and then do the 10, 16, 22, 28. Just spreading this thing out a little bit so I have a little less to deal with in terms of my graph. 34 and 40. Okay, and so as I plot this thing, again, it should be linear because they're increasing consistently. So it's like I've got a 110 is right here, 216 is right here, 322, 428, 5 would then be this guy, 6 would then be this guy. And so as I look at this thing, this is the plot of this, and I'm not going to connect it with this line. And the reason I'm not going to connect this with the line is because really by connecting with the line, I'm seeing there's points in between. And when you think about it, like if I looked at the ordered pair right here, could I have an ordered pair that was right here? Could I have 1.5 trapezoids and come up with the... Okay, no, we're increasing by whole trapezoids, so this one is discrete, it's not continuous. And remember, discrete just means that we leave this thing in terms of points rather than connecting it with a line. Continuous is where we actually connect these guys with a line because we could have values in between. All right, and that's it. For these guys, it says write an equation for each table. And so as I look at this thing, again, I'm looking for consistencies in terms of the increases. So like here, it's going up by 1s each time. So the x's are increasing consistently. Here it's going up by 1.3 each time, looks like. And so those are increasing consistently. And so when you compare the x and the y, if they're increasing consistently, it means that this thing is a linear function. And so once again, when I write the equation of a linear function, it's y equals, this one's going to be a 1.3x. Again, it's the thing that I'm adding for each, the thing that I'm adding to y for each x, and then plus the thing that's paired up with 0, which is a 0 in this one, so it's just y equals 1.3x. Okay? This one, same kind of thing. As I look at the differences in these guys, so this goes up by 1 each time. And then when I look at this guy, I might need my calculator for this one to do a little bit of subtraction in order to come up with this thing. Looks like it's going up by $3.29 each time. 3.29, and just double check that, make sure it's, going up by the same amount each time. Use your calculator to do a little bit of that subtraction. But this one is going up by the same amount each time, so this one's also linear. So it's going to be y equals, again, the thing I'm increasing by, that's the 3.29, that's going to be times the x, because again, adding that over and over again is like multiplication. And then it's going to be plus, I just look at the thing that's paired up with 0, which is the 35.27. And that's kind of like that shortcut that we've been noticing as we kind of came up with these equations. Whatever paired up with 0, that's what gets tacked on the end of this thing. Okay? And in this one, again, we're going to check the differences here. So this is going up by 100 each time. And that's a little bit different from the last couple where they were going up by 1. This guy is going down by 0.3 each time. And so they are increasing or decreasing consistently. Every time x goes up by 100, the y goes down by 0.3. And so when you think about it, it's still consistent, so it's still going to be linear. But the thing that this changes is, what am I actually multiplying by? Because again, when you look at these first two, this is 1.3 for every 1x. This is 3.29 for every 1x. This is negative 0.3 for every 100x because that's how they're increasing. So when you do this, it's going to be y equals, it's negative 0.3 per 100 x's. Okay, and that's how we have to express it. That's what we're going to multiply by the x value if we wanted to find all those values that were in between. And then once again, we're going to add the thing that was paired up with 0, the 4.5. And then from here, I can simplify this. If I actually do a little bit of division here, that's going to be a negative 0.003x plus 4.5. Okay? But again, it's not just what is this going up by, it's what is the y going up by for each x. And in this one, it's 0.003 is going down that for each x because it's negative 0.3 for 100 x's. Okay? So just be aware of that and watch out for that situation. This one just asked me to do a table of values in order to graph this thing. And so like when I look at this first one, I'll do my table of values over here. The standard values that I always start with are the -2, -1, 0, 1, and 2. And you just start plugging in. So you plug that in for x right here. So if I plug the -2 in, 2 times the -2 is a -4, plus 1 is a -3. When I plug the -1 in, 2 times the -1 is a -2, plus 1 is a -1. When I plug the 0 in, I get a 1. When I plug the 1 in, I get a 3. And when I plug the 2 in, it looks like I get a 5. Okay? And so I just plot these points. So let's say I've got -2, -3. I've got -1, -1. I've got 0, 1. I've got 1, 3. And I've got 2, 5. All right? And so they're the values I've chosen. But keep in mind, I could keep choosing values. And if you look at the graph and examine the pattern that's happening here to get from one point to the next, if I go up 2 and over 1, up 2 and over 1, up 2 and over 1, that's the kind of stuff I want to look for. And if I kept picking ordered pairs, I'd continue this pattern. We want to connect this thing with a line. Okay? The next one, same kind of thing. I'm going to do an XY chart over here. Again, I'm going to start with those standard values that I always start with, -2, -1, 0, 1, and 2. And I just start plugging in, and just be careful as you plug this in. Like here, I do 4 minus a -2 when I plug that -2 in. That's like adding the opposite, so that gives me a 6. Same thing when I plug the -1. 4 minus a -1 is like adding the opposite. That's going to give me a 5. When I plug the 0 in, that's going to give me a 4. When I plug the 1 in, that's going to give me a 3. When I plug the 2 in, that's going to give me a 2. And now I can plot these. -2, 6. It's up here. -1, 5. 0, 4. 1, 3. And 2, 2. And once again, I can kind of see the pattern that's forming here. If I were to continue to plug in ordered pairs, I'd come up with all these guys over here. I'd come up with all these guys over here. The pattern would continue. And if I take a straight edge or something and draw, wow, I missed those almost completely. Let me try that again. That's much better. Okay? But make sure you connect to these with a line, because I could get values in between. I could plug in a -1/2 if I wanted. But we can tell where that value would be just by the pattern. All right. This one I want to write a function rule. So once again, when I'm doing a function rule, it's just asking me to write an equation. That's just another way of saying write an equation is write a function rule. If you think of these kind of in a table format, because that's the way we're used to thinking, and it's okay to rewrite in a different format that makes a little bit more sense to us. And so think about these in a table. It's really the same thing. And so as I look at the increases, so in this particular table, I'm going up by 1 each time over here. So that's consistent. Over here, I'm going up by 1/2 each time. So that's consistent. And so this is a linear function. So now I know that it's a linear function. I can just go right to using that little shortcut that we have and say, okay, y equals. I know it's going to be a 1/2 x. Again, whatever I'm adding consistently to the y for each x, that's what I multiply x by. And then it's always plus whatever's paired up with 0. This time it's a 1, so it's y equals 1/2 x plus 1. All right? And again, once you have that 1/2 x, you can plug values in, and it should help you find out what you need to add in order to make the table true. All right? Same thing with the next one. If you want to kind of think of this in terms of a table, sometimes it's just a little easier to look at that way. And really, I'm going to do an extended table here to kind of illustrate this a little bit better. So I've got my x, and then over here I'll get my y. And then I'm going to do some stuff in between in a moment. Okay? So let's see. I've got 0, 3, 1, 4, 2, 7, 3, 12, and 4, 19. Okay? And the thing you should notice right away is it's not increasing consistently. Like over here it's going up by 1 each time, so that's consistent. But over here it's changing. So here it goes up by 1, and then it goes up by 3, and then it goes up by 5, and then it goes up by 7, it looks like. So the increases are not consistent. So this one is not linear. So I can't just use my little shortcut there. So here I kind of have to work backward and kind of reverse engineer this thing and say, all right, well, I see that 0 is paired up with 3. So I know that if I had a 0, I need to add 3 to whatever that thing is to get the 3. So in other words, like if I had a 0 and added 3 to it, I get the 3. Here, if I had a 1 and then I added 3 to it, I get the 4. Here, if I had a 4 and I added 3 to it, I'd get the 7. So I'm kind of working backwards. Just because I had that 0, 3, I know that my equation is going to be y equals something plus 3. And so I'm kind of working backwards. Saying, what did I have before I added the 3? Like here, I would have had to get a 9 and then added a 3 to get the 12. Here, I would have had to have gotten a 16 and then added the 3 to get the 19. Okay, and so before I add the 3, I'm figuring out, okay, what goes here? What's the pattern before I added the 3? And so when I think about the pattern before I added the 3, that's this column right here. And hopefully you can see that this column is just squaring this value. So right here, 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16. In other words, I'm taking the x value, I'm squaring it, and that gives me this middle column, and then I add 3 to it. So my equation becomes y equals x squared plus 3, because that's what I'm doing each time. I'm squaring it and then adding 3. Okay? And by breaking the table up and taking away like that addition, so we kind of break it into the pieces that we know and then try to figure out the new pattern with the pieces that are still missing for our equation. This one, it says find the range given the domain. And again, when you think about this, this is basically asking you to do kind of like an XY chart and say, all right, here's the x values we want you to plug in. Remember, domain is the x value, so it's saying, hey, plug in a -4, a -1, a 0, and a 3. All right, and see what you get. So here, I plug the -4 in. 6 times -4 is a -24, minus 5 is a -29. And then I plug the -1 in. That's a -6, minus 5 is a -11. I plug the 0 in, that gives me a 1. I plug the 3 in, that's an 18 minus 5, which is a 13. Okay? And so when it asks for the range values for this one, I just write down my y values. It's a -29, a -11, a 1, and a 13. And that's it. Okay? So domain is the input, range is the output. I plug those x values in, and I see what the y values end up being. All right? Same thing with the next one as I look at this guy. Let me section this off so my work doesn't run into itself. And so this one, once again, I'm going to do the same kind of deal here. I'm going to do an XY chart. I'm going to plug in a -4, -1, a 0, and a 3. And I just start plugging in. When I plug in the -4 in, the absolute value of -4 is a 4, minus 2 is a 2. Here, the absolute value of -1 is a +1, minus 2 is a -1. When I plug a 0 in, absolute value of 0 is 0, minus 2 is a -2. When I plug the 3 in, the absolute value of 3 is a 3, minus 2 is a 1. Okay? And so my range values are just the y values that I came up with. So the range on this one looks like a 2. And typically I'll try to write this in ascending order, so I'd probably write as -2, -1, 1, and 2. It doesn't matter if you just write down 2, -1, -2, 1, that's fine. But I'm just listing the y values that I got when I did those x values. Okay. Same thing with the next one. And let me draw a quick line to kind of section this off. But I'm going to start with my XY chart. And it's basically telling me, hey, plug these specific x values in. -4, -1, 0, and 3. And just be really careful here when you look at this guy. This is really saying y equals a -1 times x squared minus 1 times x. Okay? And so when you plug this in, maybe the first couple you don't want to try doing this by hand, and you want to actually plug this in and say -4 squared, and then minus, got a little bit of a stray mark there, -1 times a -4. And now, order of operations, I do the x one first. -4 squared is a 16, so I have -1 times 16, and then -1 times -4 is a +4, and so I get -16 plus 4, which is a -12. Okay, we just have to be really careful as we plug this in. Same thing with the -1. I would do -1 squared, and maybe I'll erase this guy, and I'll just plug it in again. So if I plug the -1 in this time, and these are far more difficult with the negatives, but -1 squared is a +1. Over here, this gives me a +1, and I get a -1 plus 1, which is a 0. Okay. And then I plug the 0 in. When you plug the 0 in, you should get a 0 out. And then I'll plug the 3 in. When I plug the 3 in, I get 3 squared is a 9, and then it becomes a -9, and then minus the 3 becomes a -12 as well. All right. So again, when I write my range values, and because some of the values are repeated, I just have a -12 and a 0. I don't write repeated values. I just say this is what's represented, and that's it. Okay. For these ones, it says identify the domain and range. And typically when we do the domain and range, I'll do like set builder notation. So here, I'm going to say x such that, just to tell myself, hey, the domain is the x values, so I'm just writing down the x values. And again, I'll try to write them in ascending order, -1, 0, 1, and 2. And then I look at the range values. That's my y values, so y such that. And I write down my y values again. I've got a 5, a 6, a 7, and a 9. And that's it. Domain is the x values, range is the y values. This one, same kind of thing. I'm going to start with the domain, x, my x values. So x is, so x such that, looks like I've got a 1, a 6, an 8, and a 14. And then my range, again, is my y value, so I'm going to say y such that. And then I just write down my y values. Looks like I've got a -2, a 0, a 1, oh, sorry. I looked up a little too quickly. -2, 0, 4, and 9. Okay? But again, the domain is the x values, the range is the y values. For this one, it says a fruit punch recipe calls for 5 ounces of pineapple juice in every quart of punch. The function p of q equals 5q represents the amount of pineapple juice needed to make q quarts of fruit punch. You have a large punch bowl that can hold 8 quarts. What would a reasonable domain and range be for the function? And so really what it's saying is, okay, when you think about this in a real-world context, think about the q values you could use. So if I think about this in terms of q and in terms of p for the juice here, for the punch, you know, obviously I could make nothing. I could use 0 quarts and make 0 juice, okay? And then I could maybe make 1 quart or 2 quarts or 3 quarts. But what happens is, as I think about this, the most I can make is 8 quarts because that's as big as this thing can hold. I don't have any bigger containers, so that's where I kind of cap off, all right? And so as I start plugging values in here, like if I plug the 0 in, I get a 0, obviously. If I plug the 1 in for q, I get a 5. If I plug the 2 in, I get a 10. If I plug the 3 in, I get a 15. And then jump all the way down to 8. If I plug an 8 in, which is the most I can make, the most I would need then is a 40. And so when you think about this, yeah, I could make maybe 1.5 quarts and kind of divide the recipe. But I noticed that my q values essentially go from 0 all the way up to 8. All right? And my p values go from 0 all the way up to 40. And really that's all I could have because I'm restricted by the containers that are available to me. All right, and so as I write this, the domain for this one would be q such that q is going to be greater than or equal to 0 or less than or equal to 8. And that's in set builder notation. And notice this one didn't specify. Let me write the other one in set builder notation. It's going to be p such that I'm either going to be greater than or equal to 0 or less than or equal to 40. Another way to express this, if I wanted to do my domain, is interval notation. I go from 0 to 8 on this guy, including each of them, so I use the brackets. On the range, I go from 0 to 40. And this is one that's much easier and much better to do in interval notation. But either one of these would be acceptable, okay? But again, we're kind of trying to just think of this in terms of the real-world context. What is it actually possible for me to use? Okay, and that's why my domain and range is changed in that one. This one, write a function rule for the area of a rectangle whose length is 2 inches more than 3 times its width. Find the area when the width is 3 inches. So this one, I'm going to go ahead and draw a picture first, and then I'll call the width w. So again, I'm going to define my variables. That's the width. And that's the only variable I'm going to use. I'm going to write the length in terms of the width. It says the length is 2 inches more than 3 times the width, so 2 inches more than 3 times the width is a 3w plus 2. Okay? And so when I think about this, then I want to know about the area, so that's going to be my other variable. I'm just going to use a for area. So I'm going to say the area equals length times width, or width times length. So it's just those two things being multiplied. And I'm going to simplify this a little bit. I'm going to distribute that w. That gives me a 3w squared plus 2w. And now this is my equation, so I've got my equation, but then it asks me to do something with that equation. It says, hey, find out what the area is going to be when the width is 3, so I'm just going to plug a 3 in for W. All right? That's the nice thing about writing the equation this way. I just have to plug one thing in for the one variable that was given. All right? And now from here, it's just a matter of simplifying, following order of operations. 3 squared is a 9, so I have 3 times 9 plus 2 times 3. And now that's going to be a 27 plus 6, which looks like a 33. And I'm going to tack some units on here. That's square inches. Okay? This one just says to find each given that f of x equals a negative 3x plus 8. And so really, when we're talking about negative 3x plus 8, if that's my f of x, whatever's in these parentheses, that's what I plug in for x. So remember, when I think about this, I think about it as f of blank equals negative 3 blank plus 8. Okay? And so if there's an x inside this blank, I have an x over here. If there's a negative 2, like in this example, in those parentheses, I put a negative 2 inside here. All right? So whatever's in those parentheses, that's what we plug in for x. And so that gives me a 6 plus 8. Which looks like a 14. And really, this just kind of tags along for the ride. It's basically saying the function, when it gets a negative 2 plugged in there, it gives me a 14. And that's what's nice about function notation. It's input and output side by side. I plugged in a negative 2, I got out a 14. All right? This one, same kind of thing. F of blank would be negative 3 times blank plus 8. Whatever's in this blank, whatever's in these parentheses, that's what I plug in over here into the function. All right? And so I just plug this in. That gives me a negative 33 plus 8. That's going to be a negative 25. So f of 11 equals a negative 25. And again, it's input, output. It's showing me when I plug an 11 in, I get a negative 25 out. Sorry, I didn't like the way my negative 25 looked. That's a little better. This one, determining if the relation is a function. Remember, a relation is a function if every input has exactly one output. Okay, so when we're looking for this, we're looking for repeated x values, and if we find a repeated x value, we got to check to see if it's with a different y value or if it's with the same y value. Okay, if it's with the same y value, then that x value only had one y value, and that's okay, it's a function. But if one x value is with two different y values, then it's not a function. And so as I look at this guy, I don't see any repeated x values, like here's a 1, a 2, a 3, a 4, and a 5. Since nothing's repeated, every one of those x values has a y value, has just one y value. There's no x value that has two different y values, so I'm going to say this one is a function. The next one, as I start looking for repeated x values, I see a 5 here and I see a 5 here. And when we look at that, you notice that the first 5 gets a y value of 2, the second 5 gets a y value of 6. Because that one x value has two different y values, this one is not a function. Okay. When I look at the next couple here, we're just looking for arithmetic sequences. It says determine if each sequence is arithmetic. If the sequence is arithmetic, we want to write a function rule to represent it. And so really an arithmetic sequence just means that this thing is increasing by the same amount each time. I'm adding the same thing each time. And so this one, it looks like to get from here to here, I add a 5. To get from here to here, I add a 5. And to get from here to here, I add a 5. So I am adding the same thing each time. So this one is arithmetic. And now I want to write a function rule. And in terms of writing a function rule, again, if you want to think of this guy kind of like an XY chart, this is the first term, the second term, the third term, the fourth term, the fifth term, the sixth term. And then from here, you just say, okay, well, it's going to be y equals. An arithmetic sequence just means I have a linear function, which means a linear function, since it's going up by 5 each time, I put a 5x here. It's 5 times the x value because I'm going up by 5 each time. And then again, the thing I add is whatever would be paired up with 0, which if I continue my pattern the other way, that's going to give me a negative 6. And so I'm just going to put a minus 6 down here. All right? It's always easier to think of this in terms of a linear function. That's the way we want to kind of think of this thing. All right? The other option would be to plug it in if you memorized this formula of a of n equals a of 1 plus n minus 1 times d. Okay? And then you can plug those values in and then just simplify. It's easier to write it this way. If you do it the other way, really the only thing that's going to change is your notation. You're going to have this instead. So either one of these functions would be acceptable to me. Okay? The next one, again, looking at the pattern here, looks like this one goes up by 3, and then it goes up by 3 again, but then it goes up by 4 that last time. So because it's not increasing consistently, this one is not arithmetic, and since it's not arithmetic, it did not ask me to write the function for this one. Okay? The next one, again, we're just looking at those increases, seeing if it's consistent. So this one, it looks like it goes up by 7. It goes up by 7 again, and then it goes up by 7 again. And so again, if I want to think of this in terms of an XY chart, here's my Y values that are given, the X values. This is the first term, second term, third term, fourth term. And then from here, if you think about this, because it's arithmetic, because it's going up by the same thing each time, I know that it's arithmetic, that means it's a linear function, so writing the equation is y equals 7 is what it's going up by each time. The thing, if I continued this pattern going the other way, the thing that would be paired up with 0 would also be a 7, so I'm going to say a plus 7. Or you can plug it into that formula once again, and you'll get a of n equals 7n plus 7 after you simplify. And either one of these would be an acceptable answer. Okay? This one, again, looking at these increases, looks like this guy goes up by 1, and then it goes up by 1 again, and then it goes up by 1 again. So we're increasing by 1 each time, so this one is an arithmetic sequence. Again, that means that this thing is a linear function. And again, if you think about it in terms of like an XY chart, first term, second term, third term, fourth term, this is X, this is Y. It's Y equals, it's going to be a 1X, and then again, if you worked backwards in the pattern one more, it would be a minus 1.5. Or you can plug it into that formula, and when you plug it into the formula, you get 1n minus 1.5. Okay? Same thing, different variables. Alright? So we're just writing a linear equation again. These guys says to find the second and the fifth terms of the sequence. So really it's just asking me to plug a 2 into this thing and then plug a 5 into this thing. So right here, if I plug a 2 into this guy, and now it's just a matter of simplifying. So a of 2 equals, and really it's just function notation. And for this particular example, when you think about it, I'll do this a different way the second time. But now I'm going to go to the fifth term. So this one, again, I'm going to plug the 5 in. We'll do it this way the first time, and then I'll show you a little bit of a shorter way for this particular example. Sorry, I want to plug a 5 in for n. And again, once again, I'm just going to simplify. And it looks like I get a 66. Okay? And again, when you think about this, if you understand what this represents and you remember the format for this thing, remember the format is this. It's a of n, the term equals a of 1, which is the first term, plus n minus 1 times 11. So n is the number of terms. A of n is that term that we're looking for. And a of 1 is the first term. So again, if you think about that, that means the first term for this sequence was a 22. And remember, d, the common difference here, sorry, I wrote an 11 here, that's going to be d. Okay, so my d value, that's the common difference. That's the thing that it's going up by each time. So when you think about this, it's saying this particular one starts with an 11 and then goes up by starts with a 22 and then goes up by 11 each time. So if you start with a 22, the next term would be 33, the next term would be 44, the next term would be 55, and then 66, and then 77. And then simply by counting, here's the first term, the second term, third term, fourth term, and fifth term, and you can see my second term and my fifth term are listed there. Okay, you could apply the same thing with the next one. You know it starts with a 2, and it's going up by -2 each time, or going down by 2 each time. So that'd be a -4 would be the next term, a -6, and then a -8, and then a -10, and you could keep going. But then right here, here's the second term, and then 1, 2, 3, 4, 5. Here's the fifth term. Okay, and so really you could do this simply by counting, or just plug the 2 in. You plug the 2 in for n, and it should give you a -4 when it's all said and done. Plug the 5 in for n, and it should give you a -10 when it's all said and done. Okay? I hope this was helpful, and good luck on your test.